Well, hello, I'm Saad Hassan, and well, just to establish a rapport with my viewers, so let me give you a brief idea about my antecedents. So, I did my undergraduate in electrical engineering from NIT Jaipur. But having said that, let me just say right at the onset that there were some parts of electrical engineering which I found to be thoroughly disagreeable, and I didn't like them. Well, then I went on to pursue a master's from North Carolina State University, Raleigh. And what I did was that in the first semester, I took up 5 courses in mathematics, and I did rather well in those 5 subjects. So towards the end of the semester, I was offered a seat, which I quite gleefully accepted, might I add. And well, maths is something that I have been in love with for quite some time, and as far as I can remember. In fact, even during those times that when I didn't really understand what mathematics was, and I realized that by saying so, I have made a very audacious claim that maybe I do understand mathematics as of now. Well, I'm not going to answer that question. In fact, one of the greatest minds to have ever walked on earth, von Neumann, said that, well, you don't really understand mathematics, you just get used to it. So I'm going to not answer that question, move past that question, and I'll tell you that why I am doing this video. What's the motivation for this video? Is that so I solved one IASA problem in the previous video, the link to which I will attach in this video as well. And it so happened that one of my friends gave me the feedback that I went over a few non-trivial things quite quickly. One of them was this Cauchy-Schwarz inequality. Now, for the sake of brevity, I'm just going to call it the Cauchy's inequality. And he said that I just went over that part quite quickly. I should have probably lingered over and maybe tried to maybe I should have taken up some more time to deal with the idea in great detail. So in this video, I'm going to take up, if you like, Cauchy-Schwarz inequality. And I'm going to take up a couple of problems, one from PRMO, which is the Pre-Regional Mathematical Olympiad, the other from Putnam. So before I go ahead and tell you what Cauchy-Schwarz inequality is, let me tell you this, that there are a few tools and few ideas and few concepts in mathematics that are very obvious. They sort of scream in your face. Whenever you see a problem, you almost as if it's almost obvious that this is the idea that you're going to imply. And then there are those ideas which are a bit subtle, and their invocation requires either a trained mind or maybe a very keen one. So I believe that Cauchy-Schwarz inequality forms quite the latter. So one of the things which my friend asked me was that, how did you know that you had to invoke Cauchy-Schwarz inequality? Because it was not apparent. And to which I said that sometimes you look for things. It just so happens that there are some tools which sort of scream and screech and announce their presence that, well, here I am, and use me to get the answer. But there are some tools that you have to, in fact, look for them. You have to assiduously look for them, and unless you look for them, you're most likely to miss them. In fact, I am also guilty of ignoring this inequality in many problems. In fact, I'll recommend at this point that if you're studying inequality or if you're solving an inequality, and if you find yourself in the middle of a problem that you can't probably solve, I'm not saying that you will be able to solve it by invoking this inequality, but if you haven't done that, then try using it favorably, right? So yeah, so you have to sometimes look out for what's there. So which reminds me of a famous scene from Sherlock Holmes that was played by Robert Downey Jr. So in one of those scenes, he is chasing this very infamous, if you like, notorious criminal who is quite used to sacrificing people for getting insights into the art of magical craft. And well, Sherlock Holmes and his aide, Dr. Watson, they go and ransack his place and finally get hold of him. And as Dr. Watson was rather imprudently walking towards Lord Blackwell, as he was, so Sherlock Holmes cautions Dr. Watson and identifies a contraption which was tied to Lord Blackwell's body which contained a pointed transparent knife, and if Dr. Watson would have walked into it, well, it would have impaled him and killed him right there, and nobody would have known about the reason because that was transparent. So, well, Watson says that, well, how did you know that it was there? To which Sherlock Holmes responded that, well, I was looking for it. So I'll say that Cauchy-Schwarz inequality, if at all it's screeching in your face that here is the problem and you have to use Cauchy-Schwarz inequality, great. And we are done. But I'll say that in many of the inequalities that we solve, try using Cauchy-Schwarz inequality, you'll find that you'll be able to solve many of them. All right. So without much further ado, let's begin with Cauchy-Schwarz inequality. So the statement says that. So let A1, A2, AN, all the way up to AN, B1, B2, BN, be sequence of reals, be sequences of reals. So all the numbers involved here are real numbers. Then, well, the Cauchy's inequality says that A1 squared plus A2 squared plus all the way up to AN squared times B1 squared plus B2 squared plus all the way up to BN squared is greater than or equal to A1 B1 plus A2 B2 plus AN BN squared, right? Something like that. That's, if you like it, the Cauchy's inequality. And as we have agreed upon that, for the sake of brevity, I'm going to refer it as Cauchy's inequality. Right. Well, nothing in mathematics is complete without proof, so I'm going to obviously provide with a proof. I recommend that you should try to prove this inequality on your own, and you can find out as many proofs as you can. So you can try it by algebra, you can try it by trigonometry, you can try it by calculus, you can try it by any number of things. So fundamentally, this inequality boils down to the fact that the square of a real number is non-negative. And so there are various ways to prove it. And in fact, I believe that one of the ways to understand mathematics is to prove propositions, or maybe try to disprove them using counterexamples. So I'm going to use one proof, and I'm going to just prove it for three numbers. That is, I'm going to prove this version, that A1 squared plus A2 squared plus A3 squared, and B1 squared plus B2 squared plus B3 squared is greater than or equal to A1 B1 plus A2 B2 plus A3 B3 squared. So what I'm going to do is that I'm going to come up with the idea of, well, cuff up isn't entirely a bad word, I must say. So A1 I cap plus, say, A2 j cap plus A3 k cap, and say that this vector B is B1 I cap plus a B2 j cap plus B3 k cap. Well, it's almost obvious that mod of A dot B will be less than or equal to mod of A times mod of B, and that's simply because mod of A dot B is mod of A mod of B times mod of cos theta. So yeah, that will be true, right? So because mod of cos theta is less than or equal to 1, so that's indeed true. So what's mod of A dot B? Mod of A dot B is going to be mod of A1 B1 plus A2 B2 plus A3 B3, and there's going to be less than or equal to root under A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared. And you can square this and you'll have your result. Right? So that's the simple proof of this inequality. Similarly, we can extend this for n real numbers by extending the inequality in n dimensions. And we can say that let there be a vector A, which is in fact an n tuple, which is A1, A2, A3 all the way up to AN. And another n tuple, which is B1, B2, and B3 all the way up to Bn. Well, so we're going to say that the second norm of these vectors, product of, rather, second norm of these vectors is greater or equal to their inner product. inner product, if you like, it's sort of dot product in which you take the component wise product and you add them up. Right? So that's, and the second norm is nothing but square root of root and even square plus c2 square plus c3 square plus all the way to n square. So there is nothing new here, and you get this, right? You square and you get the result. So you square and get the result, and you'll get that a1 squared plus c2 squared plus all the way to n squared times b1 squared plus b2 squared, so all the way to bn squared is greater than or equal to a1 b1 plus all the way to n bn squared. Well, the important part about this inequality is that, or rather any inequality, is that we must look out for those points where the equality holds. So the equality will hold, if you think about this, the equality will hold when this quantity will be equal to this quantity, or their norm will be, the product of their norms will be equal to their inner product. In other words, if you look at it here, the equality will hold only if, well, this dot product is equal to the product of these vectors, which means that two vectors are linearly dependent, or if you like it, they're parallel. So the equality holds only if when A is equal to lambda B, or some scalar lambda. That's kind of important. Well, equality holds, right? Now what I'm going to do is that I'm going to take up, so this is almost, this Cauchy-Schwarz inequality is the foundation of many inequalities, and you will see that there are many inequalities that can spring up right from here. One of the famous inequalities that are quadratic mean and arithmetic mean inequality, which says that quadratic mean is always greater than or equal to the arithmetic mean. So let's prove it. How do we prove it? Are we going to prove the QMAM inequality? Well, I'm going to put B1, B2, B3 all the way up to Bn as 1. We can do this because B1, B2, B3 all the way up to Bn, they're all real numbers. And we can choose real number according to our convenience. So we're going to choose that real number as 1. So what you get is, well, 1 square n times, and this is greater than or equal to, since B1, B2, B3 all the way to every number in this sequence is 1. So you get A1 plus A2 plus A3 plus all the way up to AN. So you get n times A1 squared plus A2 squared plus all the way to AN squared is greater than or equal to A1 plus A2 plus all the way to AN squared. Well, n is a positive number, and n square is in fact a positive number. So I'm going to divide this whole inequality by n squared. The sign of inequality doesn't change. So what you get is that A1 squared plus A2 squared plus all the way up to n squared upon n is greater than or equal to A1 plus A2 plus all the way up to AN upon n squared, right? So I'm going to turn the page over, and you'll see that what you eventually get is, I'm going to fundamentally rewrite what I've just written. A1 squared plus A2 squared plus all the way up to n squared upon n is greater than or equal to A1 plus A2 plus all the way up to an upon n squared, right? Something like that. Since these numbers are non-negative, so we can say that this is also true. And well, if you look at it, then this is the arithmetic mean of numbers. And this is the quadratic mean of numbers. And if you see, then we have proved the fact that quadratic mean is always greater than or equal to arithmetic mean, right? Well, if you were to look for a continuous equivalent, then obviously this can be extended for continuous functions as well, and you'll get something like that. So you'll get something like that. Continuous equivalent would be something like that. Well, that should be it. And well, so that's the quadratic mean, that's the arithmetic mean, if you like it. Well, so if f is the probability distribution for Maxwell-Boltzmann distribution, then you know that this is VRMS and this is V average. And it's quite a well-known fact that RMS speed is greater than the average speed for gases. So, well, but I've been a bit dishonest here, and dishonest not in saying that this inequality is true. Of course, it's true. And of course, there's an application of Cauchy's inequality, but I've been a bit dishonest in the fact that I've just taken the limits as infinity. It just so happens that we can't probably say that something which is valid for finite number of numbers will also hold when the number of numbers involved in that expression are infinitely many. In fact, we need to rigorously prove it, which is something which is in the realms of real analysis, which I will not go into. But needless to say that that's true in this case. And you'll see that our generalization of Cauchy's inequality in this form, this is a very parsimonious way of expressing Cauchy's inequality. Don't you agree? It also serves, why it serves is because of the fact that if we are talking about vector spaces, this real vector spaces, I mean, then this notation comes very handy. And when coupled with the properties of vector spaces, this will give rise to many other properties. All right. So what now I'm going to do is that I'm going to take up a couple of problems. So first problem which I'm going to take up is a problem from PRMO. That is the Pre-Regional Mathematical Olympiad. And I'm hoping that, first of all, you're going to attempt the problem by yourself. So here's the problem. The problem says that if n is a positive, a is square positive numbers, then what's the largest value of n such that this inequality holds? As always, it's entirely possible that Cauchy-Schwarz inequality doesn't readily appear in the form that you'd like it to be. So what we do is that we have to look for it. So for example, in the problem that my friend and I am alluding to, the problem about complex numbers, why I thought I could use Cauchy's inequalities is because I was looking for it. Because to be very frank, I couldn't find any other way or any other inequality to be invoked. You can solve it using AM and QM inequality as well, but I'd like to believe that AM QM inequality is nothing but Cauchy's inequality in one way. So because I couldn't find another way, so what I thought was that, well, that's one inequality which hides in the plain sight. Then why not invoke it, right? And you'll see that you will get nice results in many such problems. So coming to this problem, it's not entirely apparent that why we should invoke Cauchy-Schwarz inequality. And in fact, there are other ways to solve this problem as well. And might I ask that you should try to solve this problem on your own by employing different methods. Having said that, why I believe that Cauchy-Schwarz inequality is perhaps the perfect case to solve this problem is because of the fact that there is an a square and there is an a. There is a b square and there is a b. There is a c square and there is a c. Don't you agree this is kind of nice? Because what you get is in Cauchy-Schwarz inequality is a1 square plus a2 square plus a3 square on the left-hand side. On the right-hand side is a1 plus a2 plus a3, which is something like this. Don't you agree? So I'm going to call this entire expression as S. And I'm going to write or rewrite S as well, I beg your pardon, it just so happens that my cats are rioting in the background. So now this can be written as, oh, well, this is almost trivial. Don't you agree that this expression is as good as this expression, right? Now I want to get here. So this should be multiplied by something, b1 squared into b2 squared into b3 squared. And I'm hoping to, when I multiply this by b1 squared plus b2 squared plus b3 squared, I'm hoping that I'll obtain something like a and plus b and plus c and something squared, right? So can we try to think of that what these numbers b1, b2, b3 might be? I don't think that it's too difficult to conceive of such numbers b1, b2, b3, which when sort of introduced here will give you this result. Well, what I'm going to do is I'm going to multiply this by square root of b by 29 plus c by 31 squared, if you like, plus c by 29 plus a by 31 squared plus a by 29 plus b by 31 squared. So when this multiplied, and so this is going to give you, it is obviously going to give you, that do you identify that there's a1 squared, and there's a2 squared, and there's a3 squared, and there's b1 squared, and there's b2 squared, there's b3 squared. So what you get is a1 b1. a1 b1 is going to be simply a, and the other term is going to be simply b, the other term is going to be simply c. So this is squared, right? Do you agree? Well, I believe that this is quite encouraging given the fact that we needed an a plus b plus c on the right, and there is an a plus b plus c squared on the right. Don't worry, like we'll see what to do with this square. But for the moment, I believe that don't worry. This number is s, I believe. So what you eventually get is that s and multiplied by, can we sort of look at these brackets? What happened if you square and add them? What do you get? So that's b by 29, and this is b by 31. So b by 29 added to b by 31 is b times 1 upon 29 plus 1 upon 31. Well, c by 31 and c by 29. So you get c by 29, c times 1 by 39 plus 1 by 29, 1 by 31 plus 1 by 29. Similarly, for a, you get, well, a by 31 plus a by 29. So I believe what you get is a plus b plus c times 1 by 29 plus 1 by 31. And that's greater or equal to a plus b plus c. Now, a plus b plus c being positive, I believe that you can divide by a plus b plus c. That shouldn't be a big deal, right? Because a, b, c are positive, so a plus b plus c will be positive. So you can divide by a plus b plus c, and you get is, what you get is simply, well, s times 1 upon 29 plus 1 upon 31 is greater or equal to a plus b plus c. Well, do you see that we are done? This is a plus b plus c, something like that. Don't you agree? Right. So if you remember the original problem, they asked us to solve that s is greater or equal to n times a plus b plus c, where n is the largest positive integer. So I can't possibly say that this is going to be an integer. So I'm just going to take its floor value. So n should be equal to, so because n is the largest positive integer, so n should be equal to the floor value of 1 upon 29 plus 1 upon 31. That is going to be 14. And we're done. So that's that's the problem that we were dealing with, right? So now I'm going to take up a problem from Putnam. Okay. And so here's the problem. The problem says that, so I'd recommend that if you haven't tried this problem, I'd recommend that you should try this problem on your own so that you should get a measure of this problem before we embark on the solution. And I'd like to believe that this problem is quite nice and interesting. I'm not saying that this is the most difficult problems that has appeared in Putnam, but this is, yeah, one of the kind of nice, cute problem which can be solved here. All right, so it says that let T be an acute angle triangle. So I'm beginning with the solution. I'd recommend that you should, there's a good time to pause the video and attempt the problem on your own. In fact, I'd like to believe that if I could pass this as a common wisdom, that the way to learn anything is to do it on your own. So again, coming back to the, so I'm going to start the solution. So it says that if you have got an acute angle triangle T, so let this be an acute angle triangle. I'm hoping that I did make an acute angle triangle. In fact, as a matter of fact, I did. T. Inscribe a rectangle R. So we're going to inscribe a rectangle R in T with one side along a side of T. One side along the side of T. Okay, so something like that. So this is a rectangle R. Then inscribe a rectangle S in the triangle form in the triangle formed by the side of R opposite to the side on the boundary of T. Okay. So this is the side which is opposite to the side on this on the side of T. So we have to inscribe another rectangle here, and the other two sides are along T. So this is another rectangle, S, with one side along the side of R. So you can see that S has one of its side on the side of R. For any polygon X, let AX denote the area of X. So they're asking us to find the maximum value of AR plus AS upon AT. So, well, objective is to find, so our objective function is to find AR plus AS upon AT. In fact, the maximum value of this to maximize this. I believe that's the problem, yes. To find the maximum value, rather. So to find the maximum value. The maximum value. Right. So, well, this sounds a bit complicated, to be honest. Well, what I'm going to do is that the first thing which I'm going to do is that I'm going to draw a perpendicular from this side to this side. And I'll remember that there's an acute angle triangle. So let this angle be, as soon as you draw a perpendicular, you see that there are many similar triangles. Well, it almost goes without saying that all these triangles are similar. All these triangles are similar. All these triangles are similar for reasons which are entirely obvious, right? And I really am finding it very difficult to find the area of these rectangles, if you ask me. But what if I was able to find the area of these triangles, and if I was able to add them up? And let's assume that all these little triangles, their area adds up to delta. Let's assume that that's true. So you're going to agree that area of rectangle R plus area of rectangle S plus this entire area of these 6 triangles delta is going to be equal to the area of this triangle AT. I believe that that's quite an easy thing to understand, right? Isn't it? So what if I were to divide this expression by AT? So what you get is that AR plus AS, and that's going to be about 80, in fact, is going to be about 1 minus delta upon 80. We have divided this entire thing by 80 to get this expression, right? So if you want to maximize this, which means that you're going to maximize this, which means that you're going to minimize this. So our objective has now changed a bit. So our idea is to minimize delta upon AT. What's delta? Delta is the area of all such triangles, right? How do you find the area of all such triangles? That remains the mystery, and we haven't solved it yet. So to find the area of this triangle, so I'm going to obviously assign arbitrary lengths to the side of these triangles. So let's be A1, let's be A2, and let's be A3. Let this be B1, let's be B2, let's be B3. I'm just going to talk about one triangle and every other triangle will follow. Now, do you agree that, look at just this triangle, and we can generalize about the other 6. Do you agree that area of this triangle is going to be, so if this angle is theta, this angle is theta, this angle is theta. So if this is A1, so there's going to be A1 sine theta, and there's going to be A1 cos theta. So area of this triangle is going to be A1 sine theta into A1 cos theta. So the area of this triangle is going to be 1 by 2 times A1 squared sine theta into cos theta. Do you agree? Yeah. So talking about delta, delta is going to be equal to, well, 1 by 2 A1 squared sine theta into cos theta. Similarly, the area of this triangle is going to be 1 by 2 into a2 squared into sine theta into cos theta. And similarly, 1 by 2 into a3 squared into sine theta into cos theta. Similarly, now if you look at it, the area of this triangle is going to be 1 by 2 into b1 squared into sine phi into cos phi. Rather, b1 squared into sine phi into cos phi. It's 1 by 2 into b2 squared into sine phi into cos phi. Plus 1 by 2 into b3 squared to sine phi into cos phi. This is rather elementary, isn't it? Okay, so this can be rewritten as, delta can be rewritten as 1 by 4 times sine 2 theta. Well, so 2 sine theta cos theta is sine 2 theta. So 1 by 4 times sine 2 theta, and this is a1 squared plus a2 squared plus a3 squared. And if you like it, plus sine 2 phi times b1 squared plus b2 squared plus b3 squared. Right. As we have agreed that sine 2 theta is 2 sine theta cos theta, and sine 2 phi is 2 sine phi cos phi. Right, so you get something like that. Similarly, can we evaluate AT? AT was, if you remember, the area of the entire triangle. Now, if you see, the entire triangle can be bifurcated into two, and the area can be understood as the sum of these two parts. Right. And so, again, this side is going to be a1 plus a2 plus a3, this entire side. This angle is theta. So this perpendicular is going to be a1 plus a2 plus a3 sine theta. This is going to be a1 plus a2 plus a3 cos theta. So area of this triangle is going to be 1 by 2 a1 plus a2 plus a3 squared times sine theta into cos theta. And we know a better way to write that. That is 1 by 4 a1 plus a2 plus a3 squared sine 2 theta. Oh, well, similarly, the area of this triangle is going to be 1 by 4 b1 plus b2 plus b3 squared sine 2 phi, for a reason which is very obvious, because this is b1 plus b2 plus b3. So this ought to be b1 plus b2 plus b3 sine phi, and this ought to be b1 plus b2 plus b3 cos phi. So the area of a right angle triangle is, well, simply the half into a base into height, and you get b1 plus b2 plus b3 squared sine 2 phi. Right, do you agree? Now, the idea was to, in fact, I will minimize this about this. I got a nice feeling about this inequality, because here is this number and here is this number. We have seen these numbers somewhere. Here is this number and here is this number. We have seen these numbers somewhere. So I'm just going to invoke Cauchy-Schwarz inequality, and it says that 1 squared plus 1 squared plus 1 squared times a1 squared plus a2 squared plus a3 squared is greater or equal to, using Cauchy-Schwarz, a1 plus a2 plus a3 squared. That shouldn't be a trouble for you, isn't it? It's just a simple invocation of Cauchy-Schwarz inequality. So you get 3 times a1 squared plus a2 squared plus a3 squared is greater or equal to a1 plus a2 plus a3 squared. So like that. I'm going to multiply this inequality by 1 by 4 sine 2 theta. We can do this because 1 by 4 is positive and sine 2 theta is positive. Why sine 2 theta is positive? Because, well, it's an acute angle triangle, so theta lies between 0 and pi by 2. So 2 theta lies between 0 and pi, and sine between 0 and pi is positive. So, well, we can multiply by sine 2 theta, and it wouldn't change the inequality. So I'm going to multiply this whole inequality by 1 by 4 sine 2 theta. So what you get is, in fact, 3 times 1 by 4 and a1 squared plus a2 squared plus a3 squared sine 2 theta is greater than or equal to 1 by 4 times A1 plus A2 plus A3 squared, I believe. That's something that we have obtained, I believe. Yes. And sine 2 theta, of course. Well, what we have done for A1, A2, A3, similar process can be repeated for B1, B2, B3, and eventually we'll get that 3 times and 1 by 4 times B1 squared plus B2 squared plus B3 squared times sine 2 theta is greater than or equal to 1 by 4 times B1 plus B2 plus B3 squared sine 2 theta. And if you add these inequalities, you can almost see what's going to come. Don't you agree? So if you add these inequalities, you can see that these and these, they are going to add up to delta. So you get 3 times delta is greater than or equal to. And if you add these, you get AT, the area of the polygon T. And so you get delta upon AT is greater than or equal to 1 by 3. So, well, we have been able to find the minimum value of delta upon AT. And in fact, that was what we were looking for. So refer back to the original problem. We were interested in finding the minimum value of this because we want to find the maximum value of this. So now we can find the maximum value of this. Well, so it's not too hard, I believe. So you can say that minus delta upon A of t is less than or equal to minus 1 by 3. So 1 minus delta upon AT is less than or equal to 2 by 3. So the maximum value is 2 by 3. And we're done. Now, what we can do here is that we should also maybe verify that somewhere the equality holds that indeed 2 by 3 is a feasible region. So for the equality to hold, so equality must hold at every point, which means that as we have agreed upon that A should be equal to lambda B. So you'll realize that A1 should be equal to, so A1 should be equal to A2, should be equal to A3. So when that happens, you will see that the equality holds, right? And we are done. Because the equality holds when A is equal to lambda B, right? Is that okay? So it would mean that A1 is equal to lambda, A2 is equal to lambda, A3 is equal to lambda, which means that even A2, A3 are equal. And when they're equal, the equality will hold and the value will come out to as 2 by 3, right? And we are done. Hope you enjoyed the video, but before I part off, I will like to perhaps generalize this problem. Can you do the same problem by assuming there are not 2 but n rectangles inside the triangle? And obviously that's an acute angle triangle. And you, instead of 2, you're constructing n rectangles. And so on, right? So assume that there are n such rectangles, say R1, R2, R3, and so on. So can you find out that what's the maximum value of A of R1 plus A of R2 plus all the way up to A of Rn upon AT? That's the original problem. The answer comes out to as n upon n plus 1. Okay, that's all. That's it for this video. All right, bye.